I'd like to welcome you to the RA2 session. It's great to follow on from the ESAC. At least there are still some people remaining in the room, so that's good. No, so RA2. So we cover aerosols, clouds, turbulence, and climate. And I'm just going to quickly, and Frida and I are just going to quickly go through some quick slides on some of the things that have happened in RA2 this year and some of the news we have. We're not going to talk for very long because we want to focus on the science. So without further ado, a highlight perhaps, or you can see it as a highlight, is that we actually have two new people here. That's me and Frida, who are actually the RA2 leaders. So we've taken over now from Ilona Riepen and Annika Ekman. And first of all, we would like to give them a great thanks for all the work they did in the time previous. This is our first Bolin days, so this is the first real opportunity we've had to thank them. So we would like to do that. We will try to follow in their footsteps with some skill. To introduce who we are, I don't know, Frida, if you want to say something about yourself. You can see who Frida is. I'm Matt Salter, so I'm here at ACES-L. My background is actually as a marine biogeochemist. So I changed my life, in a sense, to come to aerosol science when I came here about 5 years ago. So I have interests across the Bolin Center, so not just in RA2.
And yeah, I'm Frida. I'm at the Department of Meteorology, and as we put down here, I guess my research interests include the large-scale effects of aerosols and clouds and their interactions on the rate and budget and climate, things like that.
So one major piece of news that we had this year was that we actually held a workshop for the whole of RA2 in May this year. Part of the reason for that was that we've held these in RA2 before, and I attended one. It was a great success. But Frida and I also wanted to get an overview of actually what was going on in the research area as we were new to it. So we had more than 30 participants from across the research area who presented both speed talks but also longer talks of their research. I think it was a great success. And it was great to see all the research that's going on within the research area. Our plan is to continue these workshops. We're not going to do it on a yearly basis, but perhaps every 2 years or so we will, have these workshops to catch up and see what's going on within the research area. How it works within our research area in terms of funding. So Annika and Ilona, when they were the research area leaders, had the idea that of an open call where money is available. The money that's available, it can be applied for by anybody within research area 2, or anybody actually who wants to collaborate or does research within RA2 from outside research area 2, can apply for funding on a rolling basis. And so far in 2017, we actually distributed money to about 11 different projects from across ACES, MISU, and SMHI. And actually, some of the talks you'll see in a moment are for people who have applied for and successfully got money from RA2. We cover things like for travel, for conferences and for visits, research visits. We also cover costs for small instruments and for hosting workshops. So if you have any ideas for workshops or things like that, please do send us an application. Money is always there, and we are always accepting applications. Yes.
We don't accept all applications without review. We always reviewing applications.
We accept people to apply, but you can read into that what you will. You have to have a good application. And so we'd like to highlight that we will continue to operate this as we go forward into 2018. And just as a quick sort of idea as to how to actually apply, you just need to send a 1 or 2 pager to Frida and I, where you actually outline what it is that you want to do, why it's actually got some importance to both research area 2 and perhaps hopefully Bolin Center as a whole. We're very interested in collaboration across the research areas if possible. Also a brief budget and how you're going to spend your money, so we have an idea of how it's going to go with the finances. With that, I don't think there's much more for us to add. We would like to focus and crack on with some of the science that's going on. So unless there are any questions, we'll go forward. Great.
So it's my pleasure to introduce the first speaker. Sorry, Professor Johan Ström from ACES. Welcome. Your slides are just coming up right here. Sådär, ja, och så finns det en pekare här.
Var har vi den någonstans?
I should say, Johan, I changed the title, not you, I did, because it disappeared when you sent me the slides. So
okay, we don't want to waste my 10 minutes here on this one. Because the inspiration for my 10 minutes here is actually something also Hansson said at the fika table. He said, how is it possible that so little black carbon in the Arctic can have so big impact? And you came with a number even on how many watts per square meter. And I was figuring maybe I could bring this up in these minutes that we will have here together. And my ambition then is to give you a gut feeling when you leave how little black carbon is and whether it has any impact in the Arctic. And to do that, I have an outline with only two bullets. It's a poor man's climate model, and since the audience is what it is, this will be trivial for you, maybe boring, we'll see. And then we'll talk a little bit about black carbon in snow. So we go directly to building up our little climate model, which is cheap, as you will find out. And you're familiar with this. We have the sun on one end and Earth on the other end, and there's a solar constant shining on us. And some of that solar light is reflected, and we call this albedo. And this is why we see Earth. So if we're interested in how much energy actually reached Earth, then we look at this area of the disk, and we can write a small formulation, which is simply the solar constant, the area of the disk, and the bit which is left after the reflection. So this is what we have to work with. And this is the yellow equation. Everything with the temperature radiates energy. And now pay attention to the wiggly lines. The reason for that is they took a long time to get into PowerPoint. Yeah, here's one. Okay, so we can actually express that into an equation. And this is it now, the pink equation. And it's simply a constant and the temperature raised to the power of 4. And over some time, you know, then we can assume that they balance each other. So the yellow equation balance the pink, or white in this case, equation. If we play with this a little, we are lucky that the area of a sphere and an area of a disk seem to have a constant ratio. And we can tidy up the equation a little bit with the lyrics and our albedo and the temperature raised to 4. Okay, so we plug in the albedo, and you know that things gets too cold. And we know the reason for that is that Earth has an atmosphere, and pay attention, more wiggly lines. So now there is more energy trapped. And we describe this atmosphere analogous to albedo. So we think of it as a reflector for thermal energy. So they look the same in the equation. So now our equation is a little bit more complicated. We have albedo on one side and the greenhouse gases on the bottom side. And we make our fancy poor man's climate model even easier or simplified. So now we only have the albedo on top and the greenhouse gases at the bottom, and some constant. And we need to calibrate it, tune it, parameterize it. So we know that with the actual average temperature of 15 degrees C and an albedo of 0.3, this GG factor pops out. So we've now tuned our little climate model. And if we make small changes in albedo or greenhouse gases, maybe this works. So we make a 1% change in albedo. Now this is average, of course, over the whole globe. And to see what happens. And we get about a 3rd degree increase if we lower it with 1%. And this 1% I will return to a little bit later, whether this is a lot or little. If we do the same trick, we test with the greenhouse gases. It's actually, most of the greenhouse gases are water vapor. And only, say, 4% is due to human activity. But we make a test scenario where we double the greenhouse gases in our simple model. And it increases temperature by 2.2 degrees. Which is sort of some number which is not 10 to the minus 5 or anything like this. So we sort of reasonable numbers. So small changes give fair changes in the temperature. We can also try a scenario on a hypothetical planet we call polar, where the average temperature is minus 15, albedo is 0.6, and insolation, the solar constant, is only 20% of that of Earth. And here is a disclaimer. Any resemblance to an actual planet or polar living or dead is entirely intentional, okay? Yeah. Anyway, if we make a 1% reduction in albedo for this planet, it's 3 times higher than for the Earth system. And if we try the greenhouse gases with our simple model, it goes bananas, yeah? So it's not the perfect model, I agree, but if you compare with other models on the market, I get fair enough mileage on this one, I think. It's a cheap one. So now to the real world. This is Kristina Pedersen. She works in Tromsø, and she's on this picture digging snow into plastic bags, which we take into the lab and melt and filter. This is from the Svalbard area. At the same time, we measure albedo with 2 instruments. We measure the light that is reflected on the snow and the amount of light that's coming from the sun, or from the sky, clear, cloud clear. After filtration, it might look like this. This is Arctic snow, and the volumes that we melted are written here. So it's about between a pint or 2 of melted Arctic water looks like this on the filter afterwards. So I have a problem eating snow. It takes away. So with these 2 informations, the concentration of black carbon, which we measure with these filters, we put it on this axis, and the albedo we measure concurrently, and put it on here, and the scale is such that 0 is a completely clean snow surface, and as the numbers increase, the snow gets darker and darker, and here we lower the albedo by 10%. Typical values in the Arctic region is on the order of 10 nanograms per gram, black carbon to water. And if we work our way up here, we see that this is approximately 1% darkening of the snow. Okay, so if we take one bag for 1 milligram of black carbon here. This is the very picture. That bag is on the picture. Yeah. So if you take this one, this is 1 milligram, and you need to have a milligram pass it on. And here is the snow to go with it also, Alan. There's another snow. That's 1 gram snow. So if I take that bag, 1 milligram, and make smaller bags, I can make 1 million nanograms bag. Okay? 1 million. And if I put 10 of these nanogram bags into 1 gram of snow, I get my 10 nanogram per gram value. This is the best snow picture I could find. But that's so. From one bag of this 1 milligram, we can make 100 tubes, 100,000 tubes, and that's the equivalent of a handball court. So I can, with this bag that I'm passing around, 1 milligram, I can change the albedo of this area, 1%. Okay. So 1%, in my view, is a big number. And if we plug it into our four-man's climate model, it actually responds with some temperature. So if you do this on a small scale, I think 1% can be very significant, although we are talking nanograms of black carbon. And so finally, I was going to make a point, but I made an error. You have 250 watts per square meter. Of course, you will have a 2.5 watts per square meter if there's a 1% of that. And the insights from the exercise we just did is that cold, dark, and icy places appear more sensitive to changes in albedo greenhouse gases, and a few nanograms of black carbon in snow appears to matter, but will not explain everything. Okay. I want my bags back.
Comment.
One of the problems with Japan's climate model is GG. That GG is not fixed. The things like water vapor or cloud feedbacks are wrapped into changes in GG. But actually, there are equally simple climate models that can be derived from actual radiation calculations that are just as simple to run, but actually have more of those feedbacks in. So I don't know why you don't use some of those instead. You get much better estimates of the actual climate sensitivity in polar regions. But also the other thing is that the one for planet polar, that darkening of the snow only matters when there's sunlight in planet polar. So that limits the effect of the black carbon. Because during lots of the year, the albedo of the snow doesn't actually matter.
And to start with, the ambition with model was actually not to simulate climate. It was to see what happens if you perturb one of the variables a little bit instantaneously without feedbacks, and which way it's heading, and if it's any near reasonable.
But I mean, we have a whole technology for climate sensitivity, which gives you good answers to this, not bad answers to it. And so it would be worth incorporating some of that into thinking.
So when we have an hour of presentation, we maybe can take that model.
We're going to move on to the next speaker, actually. So questions for the break after. And our next speaker is Abhay Devasthale, who is here, from May. Sorry. There, who's here from SMHI, where he's a researcher.
Thanks. Yeah, I would like to thank Matt and Frida for the opportunity. And I should mention that most of the work is done by my colleague Manu from the air quality group. And also like to thank Michael and Annika and Sabina for the valuable feedback. So what I would like to talk about is how basically temperature inversions control aerosol vertical distribution in the Arctic. If you are working on Arctic atmosphere, you would probably not be surprised that when you take any radio sound temperature sounding in the Arctic, the first thing that you notice is the presence of temperature inversions. So using this modern satellite data, so hyperspectral sensor, we did a survey of the inversion properties. So what's the, for example, clear sky temperature inversion frequency in the Arctic, and that's what you are looking at here. And it is no surprising that in spite of having very coarse vertical resolution from in the satellite sensor compared to radio sounds, we still get very high temperature frequency, inversion frequency over the Arctic, especially during polar winter. So it is fair to say that the temperature inversions are actually one of the most dominant meteorological phenomena in the Arctic. Now, switching to completely different thing, aerosols. So this is aerosol vertical distribution in the Arctic for over the Atlantic sector of the Arctic. So that's 20 west to 30 east and 70 north. And this is using the first LiDAR in space of Calypso is the name of the satellite. It carries a LiDAR, and we have had now almost 10 years of data from it. And it shows you the vertical distribution. By vertical distribution, I mean the frequency of occurrence at each vertical frequency of occurrence of aerosol layer at different height intervals. And most of the aerosols are accumulated in the lowermost troposphere. I mean, at the first glance, nothing really stands out here. It's just a normal vertical distribution. If I would say that this is a vertical distribution in the Southern Ocean, and most of these are marine aerosols, you would say, yeah, that's fine. It looks normal. But what makes it special is its Arctic context, because we know that there are a host of processes that are going on in the Arctic which are unique to that environment. For starters, we just saw that there is this persistent inversions hovering over the Arctic more or less all the time, especially during polar winter. So there is no, and this sea ice is, and the sea is covered with ice. So there are no local sources of aerosols in the Arctic. So where are these aerosols coming from? So obviously they have to be transported, and there are different pathways to do that. So low level transport versus elevated transport in the free troposphere that brings aerosols in the Arctic. Then we have typical scenario where clouds are capped by inversion layers, and when these aerosols are being transported, they undergo a lot of changes, aerosol optics changes, aerosol morphology changes, because they are being processed and reprocessed by clouds and humidity, etc. So what's the motivation of looking at this covariability between inversions and aerosols? Now, given the fact that we have this really strong barrier of inversions, it would make sense to see what happens to aerosols when they are being transported. As the atmosphere becomes more and more stable, what happens to these aerosols? Do they start accumulating? How do they impact surface energy budget? Do they interact with clouds? Because if they interact, they might increase the lifespan of the cloud, and that will enhance the long wave forcing. So there are so many interesting things or processes that might be going on, but we first, to start with, we don't know how basically aerosols and inversions interact with one another. What's the covariability looks like? And precisely this is what we try to do. Using two different sensors, satellite sensors, one giving you detailed vertical structure of temperature and humidity, and the other one giving you giving us the aerosol profiles. And what we did was we composited our data into different stability regimes based on their inversion strength. So we looked into 10 percentile, 50 percentile, 70 percentile, and 90 percentile. If an inversion strength over 1 degree by 1 degree grid box exceeds one of these thresholds, then we composite aerosol vertical distribution into that category. And then, so basically what you are doing, what we are going is from very mildly stable atmosphere to extremely stable atmosphere as you go to higher, of course, higher inversion strength. And another thing we looked at is what's the percentage of aerosols that end up below the peak inversion height if you have an inversion, and what's the fraction that end up in the free troposphere. So I'm going to show you just two examples because of the brevity of time. The first one is over the Atlantic sector of the Arctic, and this is during winter time conditions. And what we observed here is that as the atmospheric stability increases, we have more and more number of aerosol layers are being detected in the lowermost troposphere. So there is clearly an accumulation of aerosols going on. And it is also it's also evident in the aerosol optical depth, which consistently increases from P10 to P90. So given the fact that not only the frequency is increasing, but also AOD is increasing, we can be pretty sure that there is an extra accumulation going on, and it's not just because the relative humidity is changing and water uptake is changing. So, but what happens in the Pacific sector? So just to mention, just to give you some number, from all cases, if you just separate out the extreme stable condition, we have almost 20% increase in aerosol load in the lower troposphere. What happens in the Pacific sector during spring? Here we actually see a very different signal. As the atmosphere becomes stable, we actually have an increase in the free troposphere aerosols. So here we have a decrease in the lower troposphere, that means the increase in the upper troposphere, and this is an AOD of aerosol layers which end up in the free troposphere, and they show consistent increase. So we have two different regions, two different seasons, two very different signals. So how do we make sense of all of this? For that, we have to take a look at the different pollution pathways that occur through which the pollutants are transported into the Arctic. Generally, it is so. This is a schematic from Lowe et al. Paper, which was originally proposed by Andreas Stoll in his 2006 paper, which basically talks about three major pathways of aerosols into the Arctic. One, you could either have a low-level transport right into the boundary layer all the way to the Arctic. Now, for this kind of transport to occur, because as you know, there is this polar dome over the Arctic, and for the low-level transport to occur, the regions from which the aerosol come into the Arctic needs to be a part of this polar dome. So basically, they are usually Northern Europe and Siberia, and you can pretty much rule out North America or East Asia. Another way aerosols end up is you could have first low-level transport, and then when you hit the Arctic front, then the air masses are lifted up and kind of gradually sink into the Arctic, into the boundary layer. The third possibility is that the aerosols are already injected quite high up in the free troposphere at low latitudes. For example, warm conveyor belts or some sudden change in the circulation, and then being gradually transported into the Arctic. So what our studies, what our results seem to suggest that when we look at the Arctic sector, the mechanism one where the low level transport occurs seems to be the most dominant one, because we have a consistent increase in aerosol loading as the atmospheric stability increases, and the chances of aerosols being transported first into free troposphere and then taken down into the lower tropospheres are the probability is very low. And when it's come to Pacific sector, it's probably the mechanism 2 and 3 that are most active, because that's where we have the most accumulation in the free troposphere. So to summarize, we use the collocated data of thermodynamical variables, temperature and humidity from one sensor, and the aerosol vertical distribution in other sensor, kind of try to look how the covariability between aerosol and temperature inversions look like over the Arctic, and we see a very different signal in different. So the response really depends on which sector and which season that you are looking at. And what our study does is kind of gives you an observational basis for doing some really interesting model experiments. For example, what happens when you have such kind of accumulation, what happens to aerosol cloud interactions, what happens to the surface energy material, how sensitive these fields are. Thank you.
Thank you. Questions for Abhay?
I actually have two quick questions. One is, were those surface-based inversions or elevated inversions?
Yeah, we don't separate as of, but there are surface and elevated inversions, both included in the
And
analysis.
the inversions are cloud capped?
Usually, yeah.
Or cloud, anyway.
Yeah,
Cloud there.
yeah.
So can the satellite see through the cloud? Okay. Underneath?
No. We allowed cloud fraction, I think, up to 70%, because all we need is a hole in a cloud to look through to get the inversion, and so we are essentially a little bit biased towards clear gas condition. Yes.
If we don't have another quick question, I will turn this off. Our final speaker is Lowe, a PhD student at ACES.
Great, thank you. Good afternoon, everybody. I'm going to talk to you a little bit about some modelling work I've been doing concerning surface active components of organic aerosols and the impacts they may or may not have on cloud microphysics. Does this work? This one?
Yeah. If you, it's in the ceiling.
No, to change the slide.
Is it on? Yeah, it's on. Let's see.
Well, thank you. Yeah, so aerosols we define to be solid or liquid particulate matter suspended in atmospheric carrier gas, and they may affect the climate in two ways. Directly by scattering and absorbing solar radiation, which I won't really talk about today. But secondly, indirectly by influencing cloud microphysics as they are cloud condensation nuclei, i.e. sites for condensation of water vapor, and the composition and concentration of the CCN can have a profound impact on cloud properties. So for example, if you have more CCN in the same meteorological conditions, you can expect to get more droplets that are smaller, which will lead to a brighter cloud. So to look at these processes, I use a cloud parcel model, which simulates an air parcel from subsaturated conditions into a cloud. And it's kind of a system of differential equations coupling atmospheric dynamics and the growth of the particle size distribution. And it's kind of a nice modeling environment to use because it's very computationally efficient, which allows you to incorporate very detailed molecular scale processes and track them up to cloud scale phenomena. And they're used in developing cloud droplet activation parameterizations for global climate models. So the model is reliant on specifying a dry aerosol size distribution and its composition, which will be made up of organic surfactants and inorganics in this work, and also some initial meteorology, temperature, pressure, updraft velocity, and humidity. So you specify these input variables and run the model, and the parcel ascends and it cools, and as it cools, the humidity increases until it reaches 100%, the cloud base, and then you start to get condensation onto the aerosols quite rapidly, and you end up at the end of a simulation with this sort of blue distribution where you have a very distinct separation into two size regimes, the larger of which we classify as cloud droplets. So the theoretical underpinning of this condensational growth, the thermodynamics, is dictated by Köhler theory, which models the supersaturation at the surface of the wet particle as a combination of two effects. The Kelvin effect, which tells you about how the supersaturation at the surface changes due to the curvature of the droplets and is reliant on the surface tension. And the second term is the Raoult term, which described the lowering of the supersaturation due to having some soluble material in the droplet. And the peak of the Kohler curve is particularly important, the critical supersaturation, because if this is lower for a given particle than the ambient conditions in the parcel, then the aerosol can grow to become a cloud droplet. But in this sort of traditional, I think the formulation was from 1936, there's no explicit treatment of surface active compounds or a surface phase. And there have been numerous models to address this, but we have developed the cloud parcel model to include this compressed film scheme, which affects both the Raoult term and the Kelvin term by assuming all the organic matter resides in the surface phase. So it's effectively insoluble and doesn't contribute to the Raoult effect, but also depresses the surface tension as shown in the bottom panel here. And while the film is completely encompassing the droplet, we take the pure component organic surface tension. Of course, as the droplet grows, it starts to spread out, and you have sort of a fractional surface coverage. So we looked at 3 environments in this work. First, the Macehead coastal marine environment in Ireland, which we'll focus on mainly because it has this very unique aerosol size distribution where you have a very large concentration for the first mode and a very small concentration for the second mode. And because we had the compositional data for both modes in the Macehead simulations, we specified separate compositions for each mode. For the marine average and the boreal forest environment, we didn't have this information. So we run the model for these 3 cases, both with the traditional Kohler theory and the compressed film Kohler theory. And these are sort of the interesting outputs that we want to look at. And you can see that the dashed curves for the supersaturation humidity is lower in all cases. And this is because you have particles are activating more easily in the compressed film framework, so it depletes the humidity quicker. And as you can see, you have a greater droplet concentration in the compressed film framework in all cases again, but for the Macehead case, the percentage increase is much more dramatic. And at the bottom here, we look at the size distribution of the droplets at the end of the simulation, and you can see that, again, the most dramatic changes are in the Macehead case, and it has this bimodal structure because we specified different compositions for each mode. So to just probe a little bit more of the parameter space for this compressed film effect, here this surface on the left shows the percentage increase of cloud droplets using the compressed film framework versus the traditional Kohler theory. On the x-axis, we show changes in the first mode concentration, and on the y-axis, the change in the organic mass fraction. You can see there's a tendency for a much more dramatic effect at higher concentrations and organic fractions. So just to tie this back to some observations, a little bit crude at this stage, but I got some data from Macehead. Unfortunately, it's not co-located in time for the organic mass fraction and aerosol concentration, but these are some 70th percentiles, which kind of indicate a very small percentage of the observations actually give this dramatic effect. So just to sum up, I don't think I'll really discuss read out the 2 points, first 2 points, but the third point is we did a sensitivity analysis using this Sobel algorithm to probe how sensitive the effect is to different model input parameters. And related to the previous talk, it's really important that you get the updraft representation correct. Just using a fixed updraft scheme gives an overemphasis to the sensitivity of updraft, but incorporating a PDF sort of tapers this back a little bit. But I haven't got the final results to show for that, unfortunately. And lastly, just to speculate on a little bit of cloud seeding for geoengineering cloud brightness, is if we're missing this surface activity effect in our models, then we will expect there to be more, like a greater amount of water vapor available for the cloud seeding experiment. But this could be taken up by existing aerosols before you start seeding artificially. Okay, thank you for listening. And thank you for questions.
Questions? No questions.
Okay. Yeah.
So I mean, you're working in a cloud parcel model. How easy is it, as a person who's not a modeler, I'm asking that from that perspective, how easy is it to actually implement this on in a larger scale model, for example, to actually incorporate this effect?
So then you need to work with the cloud droplets, activation parameterizations. And I think this was done for some 2012 paper by Prisler, I think in Eckham. And they noticed that there wasn't a particularly large change in droplets globally, but there are so many different models for this surface partitioning that one model may have a very different output to another. So it's a little bit tricky. Part of the reason we use this compressed film model is because it gives a maximal effect in terms of the Raoult term, because you assume everything goes to the surface. So you can then sort of say, this is the maximum effect, and work back and try and see how important it really is.
Okay, any other questions or comments? Yes?
Are the surfactants that you're talking about the sort of thing that are produced by the secondary organic aerosols, things that are co-emitted with biomass burning? Is that where they come from?
Yes, I think so. Certainly in the boreal forest case. My knowledge of the organic fraction perhaps isn't so wonderful, but yeah, we tried various different compounds and stuff like this.
This is one of the things that plays into the question of climate effect of black carbon, because you almost always emit SOA precursors together with black carbon.
Okay.
And how much reflective effect you get from those SOA precursors versus the absorbing effect from the black carbon is the key. Is the key thing in dispute.
Okay.
Good point, and a good place to stop, I guess, and end this session. And let's thank all our speakers again. And let's have lunch, right?